In the previous video, we have seen the accumulation mode in which the gate potential was applied negative with respect to base, where base was grounded. The same case here, but in this case we are taking the gate potential is positive with respect to base, but VG is positive, but it's a small value. That's what we are taking. VG is positive, but it's a small value. Taking that into consideration, now when we apply a small positive potential to the gate, we get some positive charges coming onto the metal. So let me symbolically put it here. Some positive charges onto the gate. Then the majority carriers holes in the p-type substrate would get repelled because there is oxide here. These positive charges cannot go through the oxide. Hence, when positive charges come onto the metal, they actually repel the majority carriers holes here. They go away to the ground. How many are positive charges come to gate? Those many go to ground, so that it becomes charge neutral still. So when holes leave this region which is close to the surface, there will be dopant atoms which will now be exposed. So the net charge would be negative. Those will be the dopant ions exposed. Now let's draw the dopant density here with respect to distance x. Now the distance x is measured from here, where this is 0. The metal oxide interface is the reference origin, which is 0. We are taking here assumption that this is the thickness of the oxide, Tox, and this is the metal side, this is the oxide side, and this is the semiconductor side. Now because there is positive charge at the gate, and it would be at the interface of metal and silicon dioxide, because of the electric field they get pulled close to each other. So we have positive charge at the metal oxide interface, which would be like a line here, because there can be so many energy states at a given point on metal. Hence it will be like a line charge, or in fact if you see in 3 dimension, it will be like a surface charge. And the dopant ions here will be exposed. They will be shown like this. As we assume it is uniform doping concentration, it will be like this, and they get exposed till some distance, which I'm taking here as XD, which is depletion width. Now this charge, I'm going to take the total charge here. I'm saying the total charge, which I'm taking as Q metal, the charge in the metal. And this total charge, we take this as Q in the semiconductor S. Now this magnitude, not magnitude, the value here is minus Q times Na, because Na is the doping concentration here, Na. This is the charge density, which is given by rho V. Now once we know the charge density, we can find what is the electric field, which is given by electric field is given by integral rho V over epsilon times dx. So if we do that, we can find electric field. Let's find the electric field here with respect to x. When we integrate this impulse, we get a unit step. This, let's call this electric field in the oxide. Now when it comes to this semiconductor surface, now the area would reduce because there is a negative charge. But there is a condition that we need to apply here, because the electric field is directed from oxide to semiconductor interface in this direction. Now if you see in 3 dimension that there is a plane that is separating the oxide and semiconductor, which will be pointing towards you through the video. It will be like this. Now if you see, electric field is perpendicular to the surface separating oxide and semiconductor, which means electric field, if it is normal, We know from the boundary conditions in electromagnetics that electric field cannot be continuous at the boundary, but the displacement flux densities can be continuous. Hence I can say that d bar, which is epsilon ox times E ox, which is the displacement flux density inside the oxide, will be equal to epsilon Si times E Si. Hence I can say that electric field in the oxide will be equal to epsilon Si over epsilon ox times ESI. And in general, epsilon Si is approximately 11.7 to 11.8 and epsilon ox is 3.9 kind of. So then in general this ratio would be approximately 3. Hence we can say electric field in the oxide would be always higher than the electric field in the semiconductor at the surface. So I can say the electric field at the surface separating both, the electric field in the semiconductor should be smaller. And then once we start integrating towards xd, this is negative, hence the area should keep reducing. Hence it reduces and reaches 0 by the time we get to xd. It should be 0 when we get to xd. Now this is ESI. We know the values of ESI here and EOX relationship. Okay. But let's find the relationship between QM and this. We know that the total charge, that QM plus QS, should be 0. Because before we apply potential, it was charge neutral. And once we apply potential, it should still be charge neutral. So QM plus QS should be 0. Now in this case, we can write QM plus QS is nothing but QNA. In fact, this is minus QNA times XD. We are talking about the total charge, but if you see this, this is charge per unit volume. This is distance. This will be charge per unit area. Hence, I need to multiply this with area. Okay, which will be in the 3-dimension MOSCAP. You can see cross-section area. It is not shown here, in fact. You can imagine this will be equal to 0. This can be written as QM prime, which is charge per unit area, can be written is equal to QNA XD, because QM by A is nothing but QM prime. So we know now what is QM prime. Now we can find the relationship between ESI and the doping concentration and depletion width. If you see here, this value should be equal to the area under this divided by epsilon, because that's how it is, right, from this formula. So I'm going to find that ESI should be equal to QNA XD over epsilon of Si, because this charge is in the semiconductor. Hence, this is epsilon Si. Now, once we know the charge distribution and electric field, we can find what is the potential distribution. From the formula that potential is equal to minus integral E bar dot dl bar. In this case, we are going to take scalar and do it. So let me take a reference here. I'll tell you once I find what is potential, why I'm taking dotted line as reference here. Okay, so if I integrate this by taking this, integration of a unit step is a ramp, so it will be minus of, hence it keeps increasing in the negative direction. It will be like this. And for a triangle, you'll get parabolic kind of graph. That will be once we hit XD, it should become constant value. Now if we observe here, the thing is, here it is 0, okay. This is electric field, this is potential. Now we have to say that this potential difference is Vox, and this particular potential difference is psi s. This is the potential drop across the semiconductor, Vox is the potential drop across the oxide. Now if you observe here, what matters is the potential difference. We know that absolute potential has no meaning actually, right? So Here, as we know, the bulk is actually grounded, hence this potential should be 0. If this is 0, which means this potential at gate should be higher than this potential by this much value, which means I'm going to take now or shift this to the actual x. This is why I have taken a dotted x here, axis. Now we have potential, and this potential should be equal to the gate potential we have applied. Hence I can write here Vg is equal to Vox plus the potential drop across the semiconductor. Now looking at this figure, we can say that there is a positive charge and a total negative charge, both separated by a distance of Tox. We can say or talk about a capacitance value, which is Cox is equal to the charge separated, this is, let me write Qm, divided by the potential across the distance. C is equal to Q by V. That's what we have done. But in this case, if we know Qm, we can write Cox. If it is Qm prime, we should write Cox prime, so that we know this is capacitance per unit area. Now this is also equal to, we know what is this charge separated by, we can write this as epsilon ox divided by Tox, because C is equal to epsilon A by distance. A is not here just because Cox is per unit area, hence I didn't take the area here. So taking this into consideration, now if we want to find what is Vox, Vox can be written as Qm prime over Cox prime. Now we don't have to worry about Cox prime, because Cox prime can be found from epsilon ox by Tox. If we can measure the thickness of oxide and we know the oxide permittivity, then we can find what is Cox prime. To find what is Vox, we need to find what is Qm prime. Of course, if you look at Qm prime, we have Qm prime here. In this, what we don't know is xd. If you look at xd, if xt can be written in terms of psi s, then Vg will be directly written in terms of psi s. Why are we interested in psi s? Because Vg, if it is written in terms of psi s is nothing but potential drop across the semiconductor. Now we are trying to relate the gate potential applied to the surface potential at the semiconductor, or potential drop across the semiconductor, which gives us the understanding of what's happening in the semiconductor. Hence it is very interesting to write this equation in terms of psi s. So now let's find what is psi s. So if you see here, psi s should be equal to the area of this triangle, because this is nothing but the integration of this, right? So I'm going to write here that psi s should be equal to half times base is xd, we have defined here, base times height is ESI. So we can rewrite this as, we know ESI in terms of xd, let's rewrite this. This is QNA xd square over 2 epsilon Si. So we can rewrite this in terms of xd itself. So this will be xd is equal to square root of 2 epsilon Si psi s over QNA. Now once we know xd, all we need to find is basically Qm prime. So if we substitute this into this, we will get Qm prime is equal to, let me write here, Qm prime is equal to, if you multiply this with this, substitute xd is equal to this value, we get square root of 2q epsilon Si Na times psi s. Now once we know Qm prime, we can substitute that here and get what is Vox. So finally, looking at this, I'm going to write Vg is equal to Vox plus psi s, which can be written as Qm prime is here, this is square root of 2q epsilon Si Na psi s over Cox prime plus psi s. This is Vg. This is the potential applied at the gate with respect to the bulk, and due to this there is charge that is built upon gate and semiconductor, due to which there is electric field, due to which there is a potential difference which should be equal to the potential that we have applied here. So which means everything should be satisfying. So we have shown that this is equal to the potential drop across the oxide plus the potential drop across the semiconductor. Now, having known all these equations, now we need to find how the energy band diagram for this MOSCAP is in this mode. Now, we can understand why this is called depletion mode, because when Vg is small and positive when applied, the positive mobile charges which are holes are repelled, and there are negative ions exposed which are acceptor ions. That's why this region is depleted, hence we call this depletion mode of operation of the MOSCAP. Now I'm going to draw the energy band diagram for the MOSCAP in depletion mode. By looking at this potential distribution across the MOSCAP, we can draw the energy band diagram. But to start with, if you look at this, the potential at gate is higher compared to the bulk. So the potential difference is Vg, which means the difference between the Fermi energy levels in gate and base should be Q times Vg. Now, if potential is defined with respect to positive charge, as we discussed already, but the energy band diagrams are drawn for electron energy, which is negative, which means if gate is at higher potential, then the EF of gate should be at lower level than the P substrate, which is semiconductor. So let's draw the energy band diagram and then discuss. So to start with, the Fermi energy level of metal and the Fermi energy level of semiconductor. This is Fermi energy level of semiconductor. Now the distance between these two should be Q times Vg. That's what it is derived here, right? That's in fact the potential applied here. Now there is oxide in the middle, so I'm going to take the energy band like this. But in this case, as Fermi energy levels, initially when they were under equilibrium, they were at same energy level. Now, because we applied positive potential here, it goes down with respect to this. Hence, we have this, which means if these 2 points are like anchor points to the oxide energy band gap, which means the top edge should also have tilted. So I'm going to draw that particular thing tilted. It is tilted. This is EC of the oxide. This is metal, oxide, and this is semiconductor. This will be the potential drop across the oxide. This is Q times Vox. Now it's all about drawing how is the energy band diagram in the semiconductor. So if we see deep inside the semiconductor, this is P type, so there will be EV here. Now as we know, here the bend is upwards, which means in electron energy it should be bending downwards. So I'll be drawing it bending downwards. Let's see if it makes sense or not, right? So the whole concentration would be higher here because EF, EV are very close by. The whole concentration would reduce here. That's exactly the point we're talking about, that this positive charge would repel the holes near the surface. Hence, they go away. As a result, the band bends downwards. Now, if you look at the EI, EV, and EC are all parallel lines. So I'm going to take EI is somewhere parallel to this, like this, okay, and there is EC. This is EC, this is EI, this is EF, this is EV. Now, the overall band bend is actually given by Q times psi S. This overall band bending in the semiconductor is nothing but the overall potential drop across the semiconductor. Hence, we have written Q times Vg is equal to Q times Vox plus Q times psi S, which means Vg is equal to the potential drop across the oxide plus the potential drop across the semiconductor. Now the Fermi energy level differences would be equal to exactly the potential applied in the ideal MOSCAP. So this is the energy band diagram of the MOSCAP in depletion mode.